Hi there, Jose here. Today I'm going to show you how we can select an experimental design with blocks using the platform. As usual, I will explain you which design with blocks we have in the software. I will state the problem and I will choose a design from the catalog. What are OMARS designs? OMARS stands for Orthogonal Minimally Aliased Response Surface Designs. So you see an example of a color map on correlations on the left side of this slide. You can see that the main effects are orthogonal to each other, so they can be estimated independently from each other, but also from all second-order effects, because they are also orthogonal to all two-factor interactions and all quadratic effects. At the Effex software, we have mined hundreds of millions of OMARs, and currently we have 500,000 in the software, and 300,000 of those they have blocks. The OMARS designs, they can be used with quantitative and two-level categorical factors, and they can balance the power to detect interaction and quadratic effects and do screening and optimization with a single design. So in this case, we are going to look for an optimization experiment where we have the following goals. So we want to estimate a second-order effects model. We need a full rank model matrix with that to be able also to accommodate the blocks. We will be looking at different optimality criteria. We want a high power to detect all effects, but at the same time we want to be able to fit a meaningful model which needs low correlations between the columns in the model matrix and low correlations between effects and block. Also, the center points may be of interest. When do we need a blocking factor? When the tests of an experiment are organized in groups, and it is expected that two tests from the same group are more alike than two tests from different groups. Examples could be the day-to-day variation, where the experiments may depend on atmospheric conditions and they are not controlled. Batch-to-batch variation, where the result of the test may depend on the batch and not all batches are equal, or different machines that perform the different tests or different operators. How can we deal with a blocking factor? Well, we can treat blocking factor in two ways. As a fixed block effect, we will need more degrees of freedom if we do that. In this case, the blocks are distinguishable, and we are interested in assessing the differences between them. That could be machines, suppliers, locations, operators, or we can also model it as random effects. Random blocks are undistinguishable from each other as they are considered samples from a larger population. That could be the day-to-day variation and operators. The problem statement. We are a company that produces hearing aid devices. To label the devices, we laser etch miniature parts, and we want to optimize that part of the process. Three factors are active, which are the speed, the frequency, and the power. Not only that, we expect that there will be significant differences between the different operators, and there are 3 to 5 operators available to perform the experiment. This is the blocking factor, and each operator can perform 5 tests. The goal is optimization. Let's turn into the software and see how we can solve this problem using Effex Platform. This is the home page of the software, and it gives us access to the catalog search, which is the feature that we are gonna be using today to select a design with blocks. So we click on catalog search, then open filters, and we will specify that we are interested in three-level factors. Strategy is main effects and second order effects model, and we will click on blocking. Remember, we had 3 to 5 operators, so we are going to select 3 and 5 here, and each operator can perform 5 tests. 5 tests, And here in this drop-down, you can select how you want to treat the blocking effect. If you would like to treat it as fixed effect, you have to select extreme, and otherwise low, medium, or high. You have more information in the documentation. We're going to go with medium, which is default value. We have 425 designs with those properties, and because we have a few, we are going to use the graphical filter to analyze them. So we have designs with 15, 20, and 25 tests. Here we have different efficiencies for a second order effects model, number of blocks 3, 4, and 5, maximum correlation between the block and the second order effects. All designs that we have with blocks in the catalog are homage designs where the block is orthogonal to the main effects. This is also quite unique. And then the power to detect main interaction and quadratic effects. So let's see. We are also, of course, interested in a low correlation between the block and the second order effects. So we can impose a constraint there. We see that still we have designs with 15, 20, and 25 tests. We also want a low correlation between second order effects, so at least less than 0.5. So we are from the 425, we are in 144. And we want high power for interactions. Let's see how this changes. So there is a clear trade-off between the power for interactions and the number of tests. And so you see that power more than 0.7, then designs with 15 runs are not applicable. So power to detect quadratic effects should be also high. So we see that power to detect quadratic effects is also quite limiting the number of tests. So clearly, when we want high power, we want to increase the power, we have to use at least 4 operators for the experiment. So 20 or 25 tests. So let's go with that, and let's be now more restrictive in the G efficiency as well, because we want to predict. And that's it. Let's leave it like this. We apply graphical filters, we get 47 designs. We go to the table and we will select them all and go to the Pareto analysis. The Pareto analysis is where we can compare designs with each other easily, and we can compare up to 50 designs, and we can use the tools that we have there to get the best design. It has 2 parts, a table below and then the graphical interface with the attributes that we see here. So number of runs is of course important, as well as the power to detect interaction and quadratic effects. So maximum 4th order correlation is also important, and we can see what the recommended designs are. So 45, 46 for those criteria. We would like to add also center points into the picture. We see that 45 is recommended. So let's look at those designs, 45, 46. We can include up to 50 designs here, 45, 46. They have 25 tests each. So we would like also to see some designs with 20 tests. And we have 2, design 1 and design 2. So we are going to compare designs 1, 2, 45, and 46 to see if it pays off to increase the number of tests. So 1, 2, 45, 46, and we click on side-by-side comparison. Here we have them. So all our optimization experiments that you can use to fit full second order effects model and accommodate the block as well. And here we have the different properties. Center points, for example, design 45 has 5 center points, so has probably 1 center point per block. And here we have the morphology properties and the aliasing properties, maybe more interesting, where we have the color map and correlations. Design 1, very nice color map, where you can see that the block, which is this last row, this last column, is orthogonal to all the main effects, and the orthogonality between the block and the second order effects has been minimized. So you see design number 2, 45 and 46, so they are quite comparable. So we can look at efficiencies for a main effects and second order effects model because we are optimizing, and you can see how design 45, 46 they are larger, so logically the average prediction variance is lower, but numbers are not bad for design 1 and 2. So while the numbers were not that promising for designs with 3 operators, this is 15 runs, the numbers so far for designs with 4 operators are reasonably good. We can also look at the power to detect individual effects at this tab, the other one, where we select the model of interest, main effects and second order effects model, and we can see how the power to detect the interaction effects here and the quadratic effects, it is balanced in the sense that you get more power for quadratics at the expense of lower power for interaction effects, but this is with a signal to noise ratio of 1. So of course, if we will have a little bit more, then every power will be over 0.5 with signal to noise ratio equal to 1.5. So that suggests that design 1 or design 2, that they have 20 runs, will be the way to go. Actually, they are equivalent. They have small differences, so we could choose either of those. We chose for design 1. Remember, at every moment you can also download the report, where you can get a PDF or a Word document with all the properties of the design. We download the design, we get to the download page of the design where we can specify the name and the range of the factors and download the design in CSV or Excel format. And this ends the demo on how to select a blocking experiment. If you have any question, please reach out, and otherwise see you at the next video. Bye.